Okay, great. So SatNet. So this is, there's actually a couple different papers I'm going to talk about here. SatNet is interesting for a whole bunch of reasons. It is neurosymbolic in that what they're doing is they are learning the clauses in a MAXSAT problem. It's also interesting from a neurosymbolic standpoint because one of the big issues that came up here was the interface between the perception level and the symbolic level. And there are some terms from the cognitive sciences such as transduction and symbol grounding, and those issues came into play here in a really interesting way. Also, I thought was interesting from the perspective of using deep learning to solve an NP-hard problem. So where the forward pass here was actually the solving of a combinatorial problem, which I just thought was just really interesting to me. You know, especially in my doctoral work, I did a bunch of stuff with combinatorics. And I think that's interesting even from a neurosymbolic perspective, because as we get better at neurosymbolic reasoning as a community, some of the problems that we're going to start turning to are better addressed through combinatorial optimization. So things like objective inference queries maybe could be answered in this way. Looking at maybe more sophisticated entailment queries where your deduction process is not polynomial, which there's a lot of languages that are like that, especially for semantic web ontologies. So a lot of interesting stuff going on here. So here's kind of the organization. So we'll start with the background. So if any of you have taken a class on combinatorics, this might look familiar to you. Given n Boolean variables and n clauses, where each clause is a disjunction of literals, so atoms or negations. The output is an assignment of Boolean variables such that the number of satisfied clauses is maximized. So this is like, I mean, essentially it's the optimization version of SAT. And it's NP hard even if just clause has only two literals. And then a really common way to represent this numerically is you have some matrix M of dimensions n by m, and then some, I think the original paper uses S, and then I think some of the subsequent papers use M. So bear with us with the notation, but the matrix is a size n by m, which is the clauses by the number of variables, and you can frame this as an optimization problem. And I also threw in here a slide of another paper that just does an alternative approach using straight integer programming, but they formulate it the same way. So a version of this problem would be to partition your Boolean variables between input and output. So it's like, I know some of the assignments of the Boolean variables, and it's the rest of them that I need to figure out. And so, so we could say that this assignment for variables k plus 1 through m is given you have the input of these input variables from 1 to k and that matrix m. Okay, and s here is just the oracle function they give it to us. Later, when we talk about the forward pass of the neural framework, s here is essentially that forward pass. And of course, it's an NPR problem, so it just gets approximated, and they're using semi-definite programming. Another thing I put here is a visual variant of the problem, is one where the input is images instead of text. So now there's the added wrinkle to the problem of figuring out what those images are of, and then solving the combinatorial problem on that. Okay. So solving MAXSAT, I mean, people have been working on this for, like 40, 50 years. All kinds of stuff out there, SAT solvers and group programming. So the visual variant, the idea, doing this in an end-to-end architecture, the main intuition here in the SATnet paper was to have CNN type lower level layers to recognize the digits, and then have these SATnet layers that sit on top of it that then, essentially do this reasoning. And so Neuro ASP also does something like this, and that's what Chita will talk about in a few lessons. Now, solving the MAXSAT problem when the clauses are not known. Now, why would you want to do this? Well, you could think of this in a way as we're actually learning the instance of the combinatorial problem that we want to solve. And so the examples that are presented here, well, kind of the main one is the Sudoku game, but you could think of any game like that that is sort of combinatorial in nature, and learning the rules is kind of the canonical problem. But I think of this in terms of real world applications. I mean, you could view this as actually, in a way, it's like an induction problem. Now, the one thing that was about this paper that I didn't much care for was I think they learned like several hundreds of constraints, and they don't ever show in the paper, kind of what they look like, but I don't even know what good that would do because there's so many of them. So, there's this question of explainability that, yes, there is explainability there because you are getting logical clauses, but honestly, what are you going to do when you've got like 600 of them? From a human standpoint, that's not helpful. Where it could be helpful is if you want to do additional symbolic reasoning on top of that. So anyway, let's kind of see how they approach this. And then, so then the visual variants as well. Okay, so here is the Sudoku game, and so you've got this grid, and so you've got this grid, and the idea is to sum up the digits. So each column is in each row are summed up to the same, and there's been some work that looked like a grad student or someone was kind of messing around with this just for fun with some dense neural networks, not the visual case, but the base problem, just to see if you could just take kind of regular methods and just solve it. And, this guy was doing that around 2015 or so. The SATnet treated that as a bit of a baseline. It's kind of a neat GitHub site if you're really interested in that problem, because he studied it with the baseline methods quite a bit. Has a bunch of data that are as examples, and of course, creating a data set where you have solutions to the puzzle, and it's really easy to mask part of it and split between training and testing in that way. Okay, so let's talk about SATnet. So, as I mentioned, with the visual framework, you have these kind of CNN layers, the SATnet layers, which is leveraging ideas from semi-definite programming, and then it's providing a solution. what was really kind of interesting is within the forward and backward pass for the semi-definite part, they're actually using coordinate descent. But this is solving the optimization problem within those steps. And that's about all I have to add on this. Oh yes, and the neural infrastructure used in the visual version was the famous Linnet, but they retrained it with movements. Yes?
So you said that they are both learning the clauses and then they're trying to optimize the inputs based on the clauses satisfying the clauses. So is it one being done in the forward pass, one in the back?
So go back. The forward pass is using gradient descent over this. You have a combination of layers where you have these layers using semi-definite programming that also has internal to that coordinate descent going on, and then the CNN layers attached onto that. And that's what's assigning all the weights, well, the CNN layers for the visual variance. Once it does that, the weights that it learns, at least for the SatNet layers, those correspond with clauses. And then the forward pass executes, which is running the STP solver to approximate a solution to the NP-hard problem. And that's how it's calculating its loss function for the overall problem based on that. Because it actually goes and solves the problem. Okay, so
I have a question.
yeah,
So I just need a clarification.
sure.
So there's an MSC loss, which basically approximates the digits, and then there's the constraints which are in terms of the CNS, the other SAT problem. Is that right?
So it's just straight MSE or cross entropy loss depending on the problem variant, because what happens is the training, the first half of the data for a given training sample is a part of the Sudoku board, it's partially filled in. And then the test example is the entire Sudoku board all the way filled in. Now, while it would be maybe theoretically possible that there could be more than one solution at the other end, you know, that's not particularly likely. Okay. But as you'll see in the results, like because of the combinatorial nature of the problem, like using a neural network by itself is not going to work very well. Okay, so in the forward pass, you have, just to give some high level intuitions, you have input vector ZI. So these are the parts of the board that are filled in already. And for now, I'm just ignoring the visual parts. Okay. So ZI are digits that are actual, and so you're computing the relaxations of it. And then the relaxation, VO, is computed from VI based on coordinated descent. And then from that, they're then discretizing those relaxations. And this is, of course, really common, you know, overall way for optimization. It's the sort of thing we, when you're dealing with optimizing series of mixed integer linear constraints with discrete variables, just to do a relaxation, have this kind of conversion between the two. The back prop, what you're doing here is you're computing the derivative of the overall loss, and then U is this is derived from the gradient with respect to the relaxed output. And this is computed with using coordinate descent. And then they propagate that gradient through the rest of the neural network. And this kind of gets to your earlier question on the forward pass. Again, relaxed inputs, SDP computes the weights. We're using the weights that were learned from the backward pass, produces the outputs, and going from the relaxation to discrete, and with that computing the loss. So really the key result of this that enables us is the ability to compute the gradients within the SDP framework. So in terms of experiments in the original paper, these were some of the results that they have shown. And they, get, what looks like absolutely great results, okay? They also caveat that the visual case, that they have a limitation based on the limitation of the CNN layers to recognize the digits. And they have this argument that says, hey, the probability of a given digit correct is only, I think, like 80 or 90%. And they say, well, the best you could possibly do would only be 75%, so 63% in the visual case isn't so bad. And then they did also, did a permutated version of the problem in order to see if they could get similar results to the original version, just to show that, the overall process is not learning stuff based on kind of locality information from the game board the way a convolutional. Yeah.
How did they land on that best, theoretical accuracy?
Because what they did is they said, well, the probability for a given digit being correct was, I think it was like 83% or something like that. And then there were so many digits, so 83 to that power gives them the 74%. So yeah, so the baseline approach is basically the GitHub thing. So they said, end to end, they learned everything end to end for the visual case. The permuted rows, it was a nice experiment, as I already mentioned. And so they said they limited the number of clauses to avoid overfitting. So they limited it to 600 and it just would produce that many. And yeah, and so the quick note here is, why would the CNN fail, especially seeing that, notice that with the convolutional neural network, training numbers are fairly high, testing numbers are terrible, and then when you do permutations, both training and testing are even worse. And with a combinatorial problem, in order for it to really learn the structure of the problem, you'd have to have a lot more samples because there are, an exponential number of instances. Those are accuracy numbers, yes. You'll have an exponential number of instances, so you would need a huge amount of training data in order to actually make that work with the straight neural network approach. But follow-on work made some points, and this give you a little bit of a preview. First off is, in this case, they found that these visual Sudoku results were highly sensitive to initial weight assignments. And they said that about 80% of the time that it would totally fail due to poor initialization of weights. And I'll show you in a bit the authors of the paper. They actually did they did an interesting experiment that shows why that's the case. And it'll give us some good intuitions on this idea of transduction. The next is the output labels. Okay, so the input labels for the visual problem were a partially filled in Sudoku puzzle using the handwritten digits. But the output labels were the completed puzzle where all the digits were symbolic, even ones that were handwritten on the inputs. So the authors here said, well, this is an issue of label leakage. The entire system is inadvertently supervising learning on those handwritten digits. It sees the right answer in the ground truth results. So what happens when that goes away? And they show that the results go away pretty much entirely. And they also hit them on this argument too about, arbitrarily changing the hyperparameters. They show just oversensitivity to the hyperparameters that easily knock this solution out. Also, the training rates, so we talk about coordinated descent inside the forward and backward pass. Those have to operate at different rates than the overall rate. And I also believe that even, I think the learning rate for the gradient computation across the SATnet layers as well is also used at a different rate. But despite that, I felt the paper is still very significant. And keep in mind, the experimental results go away mainly in the visual case. So they still accomplished something I think that's fairly significant because they're able to actually learn these constraints in an end-to-end manner. No one did that before this work. I also thought, the mathematics involved in passing the gradients through an SDP solver for a combinatorial problem, that was non-trivial mathematics there. So I think that was also just kind of doing that, I think is fairly significant. And, it did significantly outperform the baselines at the time, even, though it's, some guy posting on GitHub. No one else had a neural network solution to that puzzle. And like I said, even though that's just kind of a guy who's just kind of messing around with things, it's not realistic to believe that you could use a neural-only architecture and get any kind of reasonable solution to a combinatorial problem like that. In using traditional deep learning, training.